So this is our this is our closing talk of our inaugural semester of our first SPICE speaking series. We have, Laura Brandimarte is the fourth of our four speakers, and thank you for coming the week before exams. This talk is a little late. We have connected for the first time with Rose Holman, which is an undergraduate engineering college with excellent students, and we hope to make this introduction. So if somebody at Rose Holman can tell us whether or not they can hear us, that would be good. So I met Dr. Brandimarte at Carnegie Mellon, where she worked with Alessandro Laquiste for 2 years. She is a leader in cognitive science of security, and her work always matches my aspirations that I never quite meet of what science of security should look like. Laura is particularly impressive in her quality of experiment design and her excellent connection of hypotheses to results. And you might think, oh, but isn't that true for everybody? But this is the economics of security and psychology of security. We're not really there yet, but Laura is. So I really appreciate you coming to join us today.
Jean, thank you so much for that great introduction. I don't know that I'm an expert at anything, but I'll take the compliment. It's really a pleasure to be here. Thank you so much, Jean, again, for the invitation. So today I'm going to be talking about government surveillance and the effects that government surveillance has on interactions of people online, and specifically in online social media. This is joint work with a few of my fellow CMU graduates. Like Jean said, I got my PhD at Carnegie Mellon University. So these are all people with a history at Carnegie Mellon. Luca is actually now at Washington University. Ed McFarlane is now at Minnesota, and Turim Somanchi is at Notre Dame. Before I get into the details of the paper, I guess I'll just briefly mention a couple of other papers for probably all of you, because you don't know me yet. I've done some work on the effects of perceived control on privacy. We published that paper back in 2013. It's co-authored with Alessandro Laquiste as well as George Lowenstein, who are both still at Carnegie Mellon University. And the results there were there's this paradox of control where if you give people more perceived control over the publication of their personal information, they're just going to end up publishing a lot more about themselves. So there is this unintended consequence of giving people control over their personal information. There is some other work that we published in Science. It's a review paper of how privacy is a highly context-dependent concept. It's very uncertain. People don't know about their own privacy preferences, and they don't know about the consequences of giving up their privacy, as well as malleable in the sense that companies can easily manipulate your perception of privacy to their advantage. We've done some work on privacy and security nudges. If you guys are familiar with the word nudge, it basically has to do with the idea that we give people directions of what might best fit their own interests. So we have a lot of examples in that ACM paper that came out last year about how to nudge. It has a lot of suggestions also for designers on how to nudge people towards the right privacy and security measures. And then I have some work that recently came out in the Journal of Experimental Psychology, where we look at the consequences of people's disclosures. So we have a bunch of experiments where we test the effect of the information that you disclose about yourself. And it turns out that a lot of the positive stuff that we disclose about ourselves gets forgotten very, very quickly, but the negative aspects of ourselves that we share are very sticky. So everything that puts us in a bad light is remembered forever, even if it happened 20 years ago and it was in your previous life and your previous self, but the good stuff gets forgotten very quickly. Today, so we're going to talk about some work that hasn't been published yet. I'm hoping to send it to an MIS journal. Probably it's going to go to management science or information systems research. And it's on the chilling effects of government surveillance. Feel free to stop me at any time if you guys have questions. Just let me know. So you may remember Ed Snowden back in 2013. He was this former NSA contractor who shared publicly a lot of classified material about government surveillance programs. One of the most famous one was PRISM. You'll hear this name in my presentation because that's the name that we give to our variable. But essentially, it's mass surveillance programs of both US and non-US citizens. So how did the public react to these revelations of government surveillance? Well, some of them started joking about it. So you must have seen this meme back in 2013 where everything that you post on Facebook can either be public or accessible by your friends in the NSA, only you in the NSA, or only the NSA. And then there's others that actually took it more seriously. Ed Snowden fled the United States back in 2013, and while he was giving the interview to Laura Poitras and Glenn Greenwald, he was in Hong Kong. And these are protests that actually happened in Hong Kong soon after he left Hong Kong for Russia, basically asking, demanding that then President, US President Obama canceled the accusations of treason that Ed Snowden was accused of. And then finally, there is just those that are confused. They're like, hey, what is this all about? The government has always been monitoring activity. What's the big deal? In order to give us some level of security, they have to monitor us and put us under surveillance. So what's the deal? In this paper, what we're interested in understanding is how exactly people reacted on social media. This is the results of a survey that the Pew Research Center did in 2015. Basically, what they were asking is, did you change if you're not interested with the Pew Research Center, they do this national surveys in the US where they ask for, it's a simple survey. So they ask people a bunch of questions about their privacy concerns in this case. And they were asking whether people change the way that they use technology after knowing that basically any kind of electronic communication is under surveillance by the US government. And so people said, well, about 18% of people said they changed the way that they use email accounts. 17 said search engines, social media sites, 15%. So this survey suggests that there is something that people did in order to respond to these revelations that the government is monitoring us. But we don't really know how. What does it mean? You change the way that you use your email, or that you change the way that you use a search engine. How exactly do you change it? And this is the question that we're trying to answer in this work. We're trying to answer, how did the public react on Twitter? Did they just continue with their lives tweeting like nothing happened? Or did they start by any chance self-censoring? This is what we mean by chilling effects of surveillance. Do people start thinking about what might be monitored in their social media activity and they decide not to post because they're concerned? This is the questions. And specifically, does awareness of government surveillance affect the way that people use Twitter? Do they self-censor? This is the major question that we're trying to answer here. There are other interpretations of chilling effects. Some other work looks at, for instance, how people conform to the norms if they know that they're being observed. That's a different interpretation of chilling effect. For us, chilling effects means self-censoring. Do people stop decide not to post something on social media because they are concerned about government surveillance? If there is an effect, is it a long-term or short-term one? And the reason why we're interested in this is because different kinds of surveillance, specifically video camera surveillance, has been proven to have very high, strong effects on high, strong chilling effects, but it's very short-term. It's very short-lived. There is a paper that came out in 2012 where people in Finland did this experiment where they put a bunch of cameras inside a house, and 10 people were living in the house, and the cameras were recording every second of the life inside the house. And at the beginning, you could see people really being aware of the cameras and trying to shy away. Maybe if they were wearing a robe or something. But a week later, everybody was walking around cameras naked and not caring about the cameras anymore. You just get used to video camera surveillance. So is this something that we also see in social media activity? And finally, if there is an effect, where exactly is it more pronounced? Is it within the US? Is it outside the US? Since this is a global level of surveillance, because it's about both US and non-US citizens, where is it more pronounced? So why do we care about this stuff? Well, I am an economist by training, so I have to care about the economic impacts of government surveillance. And Ed Felton, the U.S. Deputy Chief Technology Officer, said that U.S. companies may be at a competitive disadvantage when it comes to government surveillance, because if they have to abide by government surveillance laws, such that they have to provide government with consumers' data, then consumers who are not from the U.S., or maybe those that are also from the U.S., will decide to go to some other company that's not U.S.-based, who's not subject to U.S. regulations. And that might steal business away from U.S. companies. In fact, Forrester Research estimated that there have been losses of up to $180 billion due to this, or about a 25% decrease in IT records back in 2016. So there is a significant economic concern associated with the consequences of government surveillance. And also, I'm interested in this work because I care about the social function that social media have. Social media gives people the ability to coordinate and to expose their political dissent, for instance. You might remember the Arab Spring. Basically, people connected with each other via social media before taking to the streets. Same thing with the Gilets Jaunes, the Paris unrest that's just happening right now. I don't know if you guys heard about this, but it's been going on for 3 weeks. And at the beginning, people were just talking on social media about this. And they were organizing their movements on social media before taking to the streets. So this is a fundamental function or functionality that social media has had in the past few years. The problem is that if people feel that they're constantly under surveillance, social media will lose this functionality for society, because people will be afraid to speak up, people will be afraid to coordinate via social media. So social media will lose that function. And also, the existence of a lot of virtual communities hinges on active contribution. Think about forums for people with certain health-related issues, for instance. There's a lot of forums where people talk about their health problems because they want support from the community, or they want just suggestions on how to deal with certain illnesses. Well, if people, again, feel that the environment that they're in is not safe for them, it's not safe for them to talk about their health problems, maybe because they're going to be shared with insurance companies, for instance, then people will just stop talking about their health problems. And so all these communities will essentially disappear if we don't keep the environment safe. So these are the reasons why I'm interested in this problem. And I'm hoping that you guys agree that it's something that we should talk about. Now, there have been previous attempts at estimating chilling effects of government surveillance. Major work coming out of MIT, Alex Marthews and Catherine Tucker have a working paper on the effects of government surveillance on Google searches. So they have data on, it's publicly available, of course, on words that are being searched over Google, and they found that after people heard about the Snowden revelations, they realized that their Google searches were monitored, and so they stopped searching for sensitive stuff on Google. Stoichev has an experiment, but it's a fictional Facebook post scenario. So what she does is basically she says, okay, look at this post. Imagine that you have this post in your timeline. How would you react? So it doesn't really have any actual data on social media activity or interactions. Freibusch essentially replicates the stuff that Marthews and Tucker did with Google, but using Bing. So pretty much the same work. And also he looks at Tor, use of Tor. Actually, this should be not CAP, sorry, my bad. It's the Tor browser. Basically, the use of Tor has increased. Everybody familiar with Tor, right? So web browsing and browser. People started using Tor more after they heard about the revelations. And then finally, Penny looks at Wikipedia articles views. So the articles that are about sensitive issues apparently are being reached less as compared to before Snowden, before the Snowden revelation. So our work is a lot similar to Marthews and Tucker and Penny and Freibusch. But what we do is we use actual interactions on social media, specifically Twitter, and we combine a bunch of different methodologies, which I'm going to talk about in a second. So what we have is a pseudo-random sample of all tweets from 2013. What do I mean by pseudo-random? Basically, it's not a 10% completely random sample. What we have is for every minute, we have a 10% sample of all the tweets that appeared on Twitter. So it's for every minute, basically, in order to account for possible, time effects of, stuff happening more in during the day than during the night. So we have this huge sample of tweets, and what we do with these tweets is we search for what we call sensitive keywords. And I'm going to talk about the sensitive keywords in a second. But it's basically, to give you a preview, it's a bunch of stuff that the government is obviously interested in monitoring. Then we check whether the frequency of use of these sensitive keywords changed over time before and after Snowden as compared to a group of control keywords, so non-sensitive keywords. And I'll again define what these non-sensitive keywords are, but again, preview words that the government is not interested in monitoring. And then what we can do with machine learning algorithms is we look at specific subsets of keywords, weeks, and locations that are specifically affected by the event, which is the Snowden revelations. And then finally, we test whether this change in frequency of use can be attributed to the Snowden revelations. So we use a bunch of machine learning to do the first part, and then we use standard econometric techniques to do the second part. We have a very standard difference in difference model, nothing fancy. I'm going to talk about that in a second. So let's talk about sensitive and non-sensitive keywords. Back in 2011, the DHS, the Department of Homeland Security, published a white paper with a list of all the keywords that the government is interested in monitoring. And it's about 400 keywords. These are the keywords that we are looking at. So the keywords that are effectively monitored by the government. And it includes a bunch of words that have, and a bunch of categories that I have a list of afterwards, but you can imagine stuff like explosion, anthrax, flu. You might be surprised that they actually are interested in the word pork. I'm not actually sure why they are, but it's the only red flag that we have. I'm gonna say why it's red in a second. So this is the list of our treatment keywords. So the list of keywords that the government is actually monitoring or is interested in social media activity. We compare the behavior of these keywords to the behavior of a control group of words. We didn't want to come up with our own list of keywords. We wanted to use something that had been created in the past, just because it's better to do that. It's easier to defend from a literature review perspective. So the only requirements that we really have is that these words don't have to be monitored by the government. So if the treatment is being monitored, anything that's in the control doesn't have to be monitored. So we decided to go for food-related words. Now, the only issue is that food includes the word pork. So what we do is just drop the word pork, and that's the only intersection between the two sets. I'm going to talk about the other requirements of the list of control groups later on in the robustness checks, but I should tell you right away that if you've done any econometrics, you know that if you are doing a difference in difference model, you have to make sure that the behavior of these keywords, the control and the treatment, they have to be similar in some way before the treatment. And then you're interested in testing whether the treatment has affected the two groups differentially after the treatment. So we do a bunch of tests to make sure that the behavior of the control and the treatment groups are similar before the Snowden revelations. Okay. Does that make sense up to now? Okay. So this is the very simple difference in difference model. You have, imagine that this is the average number of food words that are on Twitter. This is the average number of DHS words that are on Twitter. You would expect a similar behavior before the Snowden revelations, and then after the Snowden revelations. If there is a chilling effect, what you would see is a larger decrease of the DHS words, which are the monitored words, as compared to the food-related words. And this is just a simple standard model to test that hypothesis. Basically, you have the count of word I in location J and time T as a function of whether or not the word is a DHS word and whether or not it appears before or after. I call this PRISM. You will remember this program from before. So this is just what happened in June 2013 that Snowden said this is what's going on, what's been going on for a while now. And then we have a bunch of fixed effects for the keyword, fixed effects for the location, and fixed effects for weeks. Okay, so very standard, nothing fancy econometric model. The fanciness a little bit comes in the machine learning. This is the work of my co-authors that have developed a new method to basically identify anomalous behavior, anomalous trends. It's based on multivariate linear time subset scanning. And they evolved this algorithm, this MD-LTSS algorithm, to become difference in difference subset scanning algorithm, because we needed to adjust that algorithm to the specific needs of this data sets. So the important thing to understand is that if we compare the results looking at the average treatment effect of the Snowden revelations, the two methodologies give exactly the same result. So the machine learning algorithm gives the same average treatment effect as the econometric model, which is good for sanity check, right? But with the machine learning algorithm, we can do so much more. We can look at all the possible interactions, all the possible subsets of anomalous keywords, locations, and weeks, right? So it's like my machine learning co-authors like to call it, this algorithm, it's like econometrics on steroids. So it's a difference in difference model on steroids. There's so much more you can do with the algorithm. So how does the algorithm work? It's multivariate in the sense that it integrates information from different streams of data. In our case, it's going to be different streams of keywords. It's linear in time in the sense that it's an efficient way to search for anomalies. It only grows linearly with the number of observations. It doesn't grow exponentially. And I'll explain why in a second. And then it's SS stands for subset scanning because it's a search algorithm. So what we do is we search over a subset of keywords, location, and time, and we search for anomalies, for anomalous behavior. What is anomalous behavior? So imagine we have a time series of data with locations associated with it. This is a map of the United States. Let's say that this is a location. From this location, we have two streams of data. We have the count of the observed monitored words, so the DHS words, these words, stuff like bomb, chemical, gas, screening, all the words that are monitored by the DHS. And we have a second set of data from the same location over time that's about food. So we've got stuff like banana, beer, coffee, pizza, etc. Right? So we have these two time series of words. Under the null hypothesis, there's no treatment effect. Before and after Snowden, the two groups shouldn't behave differently. They shouldn't be affected differently before or after Snowden. But under the alternative hypothesis, there's going to be a subset of locations, keywords, and time intervals, so it's the intersection of these three dimensions, that is affected by the Snowden revelations. So this is all the machine learning algorithm does. It compares expectations of behavior of treatment words, and the expectation I'm going to define in a second, but it's basically the past behavior of the treatment words and the past behavior of the control words. It searches for anomalies in that behavior, and then it tests this hypothesis of whether or not after Snowden we see a different effect or an anomalous behavior of the treatment words as compared to the control words. Okay. A few more details. So what is the expectation? So we have, imagine that we only had 3 keywords and 2 locations, okay? So you're going to have an observed value in location A for keyword 1, and you have an expected value. What's the expectation for the behavior of the treatment word after Snowden? It's got to be the control group word. So you're assuming basically that under the null, the treatment group and the control group are going to behave the same. Okay? This is your expectation. So for in a grid like this, you would only have to compare expected and observed in these 6 cells, right? So what the machine learning algorithm would do is it will tell you, hey, based on these expectations and these observed values, these particular subsets of states and keywords are especially anomalous. So maybe the difference between these 2 is too high, or the difference between these 2 is too low, or something like that. So the machine learning algorithm searches for these anomalies based on comparing the observed value with the actually expected value, right? Now, in this simple case, it's not hard to find the anomalous behaviors because you only have order of 2 to the 6th power combinations, right? You have, this cell, then these 2 cells, these 3 cells, these 4 cells, these 5 cells. You only have so many possible combinations of these cells, right? So you don't need any fancy machine learning. You can actually count them and see which one is the most anomalous. The problem is that we have about 800 words because we have about 400 from the DHS, about 400 from the food words. And then we have it for about 50 locations, so across the United States and outside the United States, and for when we don't have information about the location. And we have about 30 weeks of data. So imagine the combination of all this, all the possible combinations is all the order to the power of the product of this, which isn't, we can't do that. So that's when the machine learning algorithm kicks in and it uses MBLTSS, so linear in time. What does that mean? So how do we efficiently search across all these possible subsets? Well, we use a priority function. It's just a function of the values that are observed and expected, how different they are from each other. We order the locations. We have about 50 locations, depending on this priority function. Once we have the order of anomalies, so which are the most anomalous, we don't need to give a score of anomaly to all the possible combinations. Once we order them, we only need to give a score of anomaly to the top k locations, where k goes from 1 to all the locations that you have. The intuition behind this is that once you've ordered all the possible locations by level of anomaly, you are guaranteed that, for instance, if you take the first, second, and third ordered location as a subset, it's guaranteed to be more anomalous than any other combination. For instance, the first, the second, and the seventh, or the first, the second, and the fifth, or the first, the second, and the last. You order them based on the level of anomaly. You don't need to scan through all of them. You only need to scan through n of them. So for us, it's 800. So that's why the algorithm is linear in time. It only grows linearly with the number of observations and not exponentially. Because you don't need to calculate all the possible combinations. You only have n combinations. So for us, it's about 800. Yeah.
Go back. So we're defining anomaly as fair expectation and then the observed difference compared to all other fair differences.
Right.
Not, the anomaly is not what I expected, but it's what I saw. The difference, just the difference between that.
It's not really just the difference. It's a function of the ratio, actually, but it's not just the difference. I oversimplify things, but it's a function of the ratio between observed and expected value.
But
You can think of it as the difference. Honestly, it doesn't really make much of a difference. It's a little bit more complicated, but you can think of it as that.
what I'm not understanding. So for a specific keyword, I expect to see this count and then I observe this. Why just the difference is not then? Since you said that the difference is also too small, then this behavior is anomalous. But I don't get it.
So if let's say let's say I consider the word bomb and the word beer, right? Let's for instance imagine that I only have these two words. So for me, the anomaly would be I observe the word bomb go like this. Sorry. Okay, I observe the word bomb go like this. Okay, before Snowden. And then I observe the word beer going like this. So I see that they sort of behave the same, so they're a good match for each other, right? The anomaly comes if I see a big difference on average after. So if I see that there is no difference here, but that there is a lot of difference here, then that shows up as an anomaly, right? Here, I see that there is this big difference, right? Before, it was like this. Why is that the case? Why was beer not as affected by the treatment as bomb, for instance? That is what I'm talking about in terms of anomaly. The algorithm looks for weird differences in this part after accounting for the difference before. So I don't care that there is this much difference if this was the difference before and after, right? It wouldn't matter to me that there is, a difference in the count of beer and bomb. Yeah, sure, they're just different, right? What I care is why did it change? Why did the difference change after Snowden? Before it was this much, now it's only this much. But what happened here?
So
Does that make sense?
Yeah. So the difference between these two words and the difference after,
Exactly.
the difference is that significant.
Exactly. Exactly.
CDP has to be high, the difference before and after.
Right.
So I don't want to, since you say the difference, here difference is either high or low.
Right.
The low part I will not.
Right. It's basically, so it's taking into account the history of a word. How does a word behave after? So taking into account its past, what does the future look like? If you think that we are now today at Snowden, right? We have a past and we have a future. So we compare the future of two different words, taking into account the fact that they have a past. So they have a certain behavior in the past.
I have a simple question. Like, do you regularly update the list of AHS word, or is just the list that you showed?
Yeah, it's just that one list. It was published back in 2011. Yeah. Okay, so now, do you guys get why this is linear in time? So why this algorithm is efficient? Because we couldn't possibly, it would took centuries to search for all the possible subsets of 800 keywords, 50 locations, and 30 weeks. It would be impossible to do. But with this algorithm, which is called MBLTSS, we can do this because it's only linear in time. So we only have to look for certain subsets, not all the possible subsets. We had to expand on, actually I have this. So we have to expand on the MBLTSS algorithm because of the necessities of this word, so we call it DIDSS. So if we only had one keyword, here's what we would do. We would simply sort the locations from highest to lowest level of anomaly. Then we would search for groups consistent of the top K, and that would be the highest priority would be certainly one of these, and it would be as simple as that. The problem is that we have tons of keywords to do this for. So the algorithm proceeds in this fashion. So you have a bunch of keywords, right, and a bunch of locations. What you do is you start from a randomly subset of keywords. Let's say these 5 keywords. And then you ask the algorithm to search for the most anomalous locations for these particular keywords. So you do this. Let's say that the algorithm finds, okay, these 4 locations are the most anomalous for those particular keywords. Okay, once we've done that, what are the most anomalous keywords for these 4 locations? And you iteratively do this, you find these 3 keywords. Then for this, you find the most anomalous subset of locations, and you go on and on. So you iterate these steps until there is a convergence in the algorithm. And then you have to repeat this for many times, because I said at the beginning, we only start from a randomly subset of keywords, right? So in order to guarantee that you're reaching a global maxima, not a local maximum, you need to redo this a bunch of times with many random restarts until the algorithm converges. So this is how the algorithm works. We have, in terms of data, we have, I said about 12 months of tweets. It's about 18 billion tweets or 80 terabytes of data, which was quite a challenge to handle. We have 22 weeks before the Snowden revelations and 29 weeks afterwards, because the Snowden revelations started on June 6, 2013. That's the first day that Glenn Greenwald published the article on The Guardian. So what we have is basically we consider our week 0 to be June 6 through 12. The reason being that it's not like the Snowden revelations happened on June 6. We started hearing about these government surveillance programs on June 6th, but then they kept on coming. Actually, we don't even know if they're done yet. Their new documents are still coming up now, so we're not really sure. But we consider the first week the week that had the highest impact, because it's when people, for the first time, realized that the government was monitoring their activity. So we have a nice split between before and after Snowden, just because we got lucky. So Snowden happened to do this in June, and so we just got lucky there. And this is to show you what's the behavior of these words. So you see that this is not considering any fixed effects. This is just the average counts of the keywords in logs for the food-related words and for the DHS-related words. Okay. So it sort of seems steady. Nothing seems to be going on. It's pretty much constant over time, right? There's no trend that we can see visually, which is good for us, actually, because we don't have to worry about time trends. We do control for time trends, of course, but we don't have to worry about that. So what we do is we first run the simple model, the simple econometric model that I told you before. So we take the count of each keyword as a function of whether or not it's a DHS, so it's a monitored word, and whether or not it's before and after Snowden. And we find that across all possible locations, we have a decrease of about 0.8%. So about 1% decrease of the monitored words as compared to the control groups, to the food words. So what that coefficient is telling you is that people started using the monitored words 1% less than the control group, than the food words. So if there is a decrease in the control group, well, the decrease in the DHS group is bigger by about 1%. Okay. Then what the algorithm told us when we ran it is that the most anomalous subset of locations only included US states. So we started thinking, okay, what happens if we subsample the data based on location? And what we find is that indeed in the US, the effect goes up to a whole 1% point. Outside the US, it's nothing. It's positive, but it's nothing. And if you consider the data where we don't have information on the location, it's a positive 0.4%. What do you think about that? Why do you think that we see a positive here and a negative here?
So that column, can you explain that column again?
This one here?
Yeah, what's the
imagine,
no location?
These are tweets, right?
Yeah.
So it depends on the user whether they opened or closed the location. So if the location is visible to Twitter, it's their setting, right? They set it that way. We can't do anything about it. This column is for the tweets that don't have a location associated with it.
So I guess they're less concerned about privacy.
Right? I mean, the way I would interpret this is obviously, speculation, but maybe the people that hit their location feel more comfortable sharing because they know that they're less likely to be monitored. If the government were really monitoring the US citizens, maybe the fact that they're outside the US or that they hit their location altogether makes them feel more comfortable sharing. So this is all speculation, of course, but I think it was interesting. Once we subsampled across locations, we find very different effects. Negative here and positive here. So I thought that was worth a remark. And also, the most anomalous subsets of words included words like that had to do with weather, emergencies, and disasters, and health-related words like flu, that kind of stuff. So for us, if you think about it, that is not so interesting because remember, we are comparing something from January to June to something from June to December. Well, hey, it's not really interesting that it rains a lot and it snows a lot in January and it doesn't snow a lot in August and September, right? So if the effect is only driven by this kind of stuff, these kinds of words, then how can we make an argument that this is about privacy? Not really, right? It just happens to snow more in January than it does in July and August, right? So what we do is we take all those words out. We cut our sample by all the about 150 words that have to do with health-related issues like flu and stuff, and weather and disaster emergencies. And when we do that, we still find overall a significant effect. It's basically the same. It doesn't change much across the different locations. So the effects are pretty consistent. Here we see a small increase here, but pretty much it's consistent. So even if we look at words, I'm going to show you the categories, but they are cybersecurity, infrastructure security, national security, terrorism, and something else that I forget. There's 7 of them, but I have them from before. So all of these keywords are words that are sensitive because the government is actively monitoring them for stuff about security and terrorism. So these are the words that are relevant to us. And we still find the same effect if we only focus on those words. Next step is maybe you're thinking, wait a minute, who cares about a 1% decrease in the average word? Well, so these are all the categories: cybersecurity, domestic security, infrastructure security, terrorism. Agencies means stuff like CIA, NSA, that kind of stuff. Hazmat and nuclear, southwest border violence. So these are the categories of words that we have now in this data set. Even just considering these and not considering the health and weather, look what happens when you aggregate across categories. It's about, on average, a 14% decrease for each category, on average. It's a big effect. So word by word, it might not add up to much. It's about a 1% decrease per word. But when you start aggregating through categories of words, you see about a 14% bigger decrease in the monitored words than the non-monitored words. So that's pretty substantial. And again, if we do this by location, we see pretty much the same result, except this result is not significant anymore. So this is what we're looking at here. People that have their location enabled on Twitter and are located in the US are a lot concerned about using certain keywords, sensitive keywords on Twitter. Other results that came out of the algorithm, how am I doing on time? Should be fine, right? Yeah. Time intervals, significant across the entire post-revelation period. So we see a significant decrease in these words throughout June through December. But it's most significant over weeks 6 through 12 after Snowden. So what that means is that basically the first revelation started coming in around June 6. People started hearing about this stuff, and they didn't really react significantly on Twitter. Once they realized that this was going on, and once people started talking about this more and more, by week 6, so we are about end of July through, that's a tough, so end of August, beginning of September maybe. So weeks 6 through 12 after June 6, it's the highest, the peak of the effect. So that means to me, I think I've read somewhere that the average attention span of the human being is like 7 seconds or something like that. And it's when they're on a website, and I think it is comparable
of the current
to
generation.
What's up?
Of the current generation, the young generation today.
No,
I'm just kidding.
No, that's us.
That's the generation of internet users.
Yeah.
Generation of internet users. And I think it's the same as a goldfish. Attention span of a goldfish. I don't know if you guys read that statistic somewhere, but I think I did. So if the average squirrel. So if you believe that statistic, where we don't really pay much attention to stuff happening online, and there's fads that probably last a day or two, something that lasts for about 12 weeks to me suggests that it has a long-term effect rather than a short-term effect. Finally, the algorithm finds that there is a very weird behavior of the food-related words starting around week 22 after Snowden, which is just around Thanksgiving. So starting in Thanksgiving, and then comes December, Christmas, it's all the festivities, so people start talking about turkey and potatoes and chocolates and start talking about that a lot. So the behavior of the food words starts going really weird after that. So what we decide to do is cut the time period to 22 weeks after Snowden. So we don't even have to worry about weird behaviors of food-related words after Thanksgiving. And even then, the results are exactly the same. So it doesn't change much. In terms of locations, the subsets of locations that the algorithm identifies as being most affected is, as I said, the US, but interestingly, blue states. What are the blue states? We define blue states as the states that voted, that had a Democratic majority in the last elections just before this, which was the midterm in 2012. So those for us are what we consider the blue states. Now, I don't know if you have ideas on why that might be the case, but again, here it's just speculation. So we're not really trying to get at why the blue states might be more affected. If we try to control for some stuff like, I don't know, education, exposure to media, exposure to internet use, or maybe if we start controlling for that, that will go away, which means that the blue states are just on average, happen to be on average on a higher educational level than the red states, but it's all speculation. We don't really know what happened, but it's interesting. So did government surveillance affect the way that people use Twitter? Yes, it decreased overall about 0.7% on average per sensitive keywords, which aggregates to about a 14% decrease of the average category of monitored word. If there is an effect, is it short-term or long-term? I would argue that it's relatively long-term if compared to any other online activity that people do. Interestingly, the chilling effect appears to gradually increase right after Snowden, and then it starts decreasing. But again, it's still significant throughout the entire post-Snowden period. And where is it more pronounced? It has definitely a disproportionate effect in the US, and it seems to be disproportionate specifically in states, so those that had a Democratic majority in the 2012 midterm elections. So as I mentioned, we need to do a bunch of robustness checks. So we need to check that the behavior of the DHS words is similar to the food-related words before Snowden. So what we do is two things. We do one test, which is called the placebo effect, or the placebo test. So if you imagine that you move the Snowden revelations before, right? Imagine that something, let's not call it Snowden, but an intervention happened before Snowden. If we start seeing a decrease even before, then it means that this effect is not led by Snowden, right? It must be led by this other thing, this other intervention that happened that we don't know what it is, but it happened. So it's important to understand whether the decrease really started here or whether it started before. So that's called the placebo test. And the other test that we need to do is what's called a parallel trends test assumption. So you're assuming essentially in any difference in difference model, you're assuming that these two guys are parallel or almost parallel before the intervention of interest. So these are the two tests that we do, and we use machine learning to do it. So what we do is we basically shift this intervention. We pretend that this thing didn't happen here, but it happened before. And then we test whether we still see an effect, and we don't, luckily. So controlling for the decrease afterwards, it only happens starting from here. And then the other thing we need to do is, once we shift this event, we can test whether at all possible times these two look parallel to each other, or if there are any anomalies, again, before Snowden. So what the algorithm does is, for all the possible weeks before Snowden, it searches, so before we were looking for anomalies after, remember? Now we're looking for anomalies before. So we're saying, do the food words really look alike, or really look like the DHS words for every time period before the Snowden revelation? Because otherwise, if they don't, we don't have a good control group for our food, for our treatment group. So what we do is we find the words that are anomalous. There are some of them that really look different from the DHS words, so we need to take them out. So we take out the words that are anomalous before, and we rerun the study again. Actually, the coefficient goes up a little bit, but the results are basically the same. They're consistent. So we run the difference in difference subset scanning over time intervals before to find evidence of violations. So the contribution there is that typically what people do to test for that hypothesis, you can't really test for parallel trends in econometric. All you can do is try to run a bunch of interactions effects and see if you see anything weird. But we found a way to do this, from a theoretically oriented way, more formally. So we use machine learning to rigorously check for individual anomalies across the two groups. Okay, so I'm done. We were the first that we are aware of, the first to conduct an empirical study using actual social media data. This is what's called a natural experiment. So we use an event that just happened. It just happened. People, Snowden decided to reveal this in mid-June. So we used that as an intervention that we didn't control. So that's why it's called a natural experiment. So we conducted an empirical study to test whether this event had any repercussions in online social media activity, and we find that indeed government surveillance has a chilling effect on Twitter behavior, the way that people use Twitter. We attempted to understand whether there was a heterogeneity in the effect. So if we only did econometrics, all we could get at is an average effect across all the possible keywords, all the possible locations, all the possible weeks, right? But because we have machine learning, we can do that on steroids. So we can identify heterogeneous treatment effects for specific subsets of keywords, locations, and times. And we had to build our own machine learning algorithm to do this, modifying existing work to identify heterogeneous treatment effects. And we do think that government surveillance has far-reaching implications because the effect that it has on all kinds of virtual communities. The one thing that I would like to mention is that there has been a lot of talk about using metrics such as the number of people that sign up for Facebook after Snowden, or the number of people that sign up for Facebook or cancel their Facebook after Cambridge Analytica. And then people say, hey, because that number didn't change much, then it means that people don't care. Well, I'm trying to challenge that this paper tries to challenge that hypothesis because it's saying it's not about the numbers of people that sign up for a service. It's the way that they use the service that changed. So we can't really say that people don't care about their privacy because they didn't cancel their Facebook profile or because the same number of people started joining Facebook afterwards. That's not really the metric that we should be looking at. We should be looking at actual behavior. So as far as we know, we are the first ones to try to do this and try to address that from that perspective. So we did that. And so now I just threw it out for questions.
Did you do this in R or SPS?
Slide on.
Are you looking for collaborators? Are you interested in sharing the code in the method with other domains?
Definitely. So the method, I mean, it's the method itself has been published. So MDL TSS, it's published and it's publicly available. This we had to tweak. So the did SS, I didn't write it personally, but I wouldn't think that my co-authors, wouldn't think that Ed or Sriram would keep it a secret. I don't think so. So yeah.
So the other kind of natural experiment we are observing is Facebook, and you're like, people didn't believe their Facebook profiles, but Facebook already has your profile, right? This is actual behavior where you choose not to share information, whereas Facebook profiles have, the barn door property. What good does it do me to go back and delete my Facebook profile? Also, Twitter releases a statistically valid, Twitter is public data, whereas Facebook, we're depending on Facebook to tell us the data accurately. And I feel that anyone who, you see, if you've updated your Bayesian priors about the integrity of the Facebook in the past year, you would not expect your data to be accurate. Wasn't that polite?
I 100% share your concern, Jean. I really believe that that's the case. I think that, so the genie at this point is out of the bottle, right? So what can somebody who is already on Facebook do at this point? To me, all you can do is just not give them any more data. But what you've done in the past, it's been recorded and it's gonna be in there forever. In fact, there is no such thing, you will know this, so there's no such thing as deleting your Facebook account. You don't delete anything, you just deactivate it. And all you have to do is for someone to invite you again, to just click a thing, go through your security questions, update your security password, and your Facebook is active again. So there's no such thing as deleting Facebook, unfortunately.
And if you just walk away from it, you disconnect your connections, then somebody else can connect. And you will not know about it. So like, it seems like time and number of messages, both of time spent and number of messages. But you can't get that
Exactly.
accurately.
Exactly. So one, you can't get it because it's proprietary, of course, and unless you get Facebook to work with you, you won't. But I agree with you also, like how accurate is that? I don't really know. Plus, I don't know if you remember, but I want to say a couple of years back, they started rolling this thing with advertisements within the messages. So you'd have to, if Facebook gave you that data, you would have to parse also the stuff that is not really interactions between users. It's just interactions with a brand. Because you would get advertisements within your conversations within Facebook. So there's also that complication. But I 100% agree with you. I don't know that I would trust, Facebook to release actual.
Easy to implement. All they have to do is increase the number of ads in your messages, and then they can report to investors honestly the timelines and number of messages has increased.
And they have all kinds of algorithms to increase interactions anyway. So what they do with the selective feed that they do is they maximize the probability that you will interact with the platform. That's their interest, right? They want to maximize your interaction with the platform, and so they show you the stuff that is selected for you so that you're more likely to interact with it. So in a way, it's really hard to answer that question with Facebook data. I agree with you. So the other thing is that as you said, Twitter is public data. Most of it is, so the average Twitter profile is 100% public. Some people have decided to close their accounts in the sense that you have to request my permission. So if I had a private Twitter profile, you would have to request my permission in order for you to follow me. That's as far as it goes. But once you follow me, you can do whatever you want. You can text me, you can retweet me, you can do all kinds of stuff. So, but the average profile on Twitter is 100% public. So to me, this question is especially interesting because let's compare these results to the results on Google search engines, right? You would think as a user, unless you knew that the government was monitoring you, you would expect this stuff to be private between yourself and Google, right? So you wouldn't necessarily be affected if the government is monitoring you because you would expect privacy. To me, this result is interesting because you expect less privacy on Twitter, right? You know that you're building a public image of yourself and that your information is out there for everybody to see. So to me, it's really interesting that we do find a chilling effect in this respect where there should be no expectation of privacy. And we still find a chilling effect even in that domain. So I think that was really cool too. Yeah. Oh, sorry, let's go here first because I talked to you before, but I'll go to you next.
Yeah, I'm trying to see the model. So you have like how is it designed?
Oh, that's just the limitations of it. We have 2013. That's all we have. We have data from 2013. We just got lucky that Snowden happened right in between. So we sort of have the same amount of time before and after. But that was just luck. Yeah, we didn't control that.
Also, trying to how you
So we have about 18 billion tweets from 2013. And then what we have to do is we searched for specific keywords and recorded the counts for each specific keyword. So our data set, the final data set that we use is basically, imagine it's a grid of 800, so let's say the first keyword is bomb, okay? I don't know, actually the first keywords for some reason is 2600. I don't know what that is, but apparently the government is interested in 2600. I don't really know what that means, but so you have 2600 and then you would have a lot of locations, so you would have Alabama, Alaska, Arizona, blah, 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 outside of the US, no location information, so you would have all this stuff. 2600? What's up?
You haven't looked up 2600?
No, what is that?
It's an old blog metric, like the original hacker. Like,
There you go.
before there was anonymous.
Thank you.
2600 is a throwback to the days of listening to phones.
It happens apparently. At least on Twitter, because they're interested in seeing it. So
No, I mean, it was a group.
yeah.
So,
So
I guess if you refer to them, you're probably pretty embedded in hacker.
okay. Yeah, I won't pretend I am because
I'm not even, I'm just,
yeah. But so that's what the data looks like. It's a grid, it's a panel. So for each word, you would have a bunch of locations and then weeks as well. So we have 22 plus 29. That's about 30. That's about 50 something times. So for each of these cells, we have a count. So how many times did this keyword appear in this location in this week? Then in this location at that other week. Then in this location at that other week. And then in that other location. And so on and so forth for all the possible words. So it's counts. You first and then I'll, yeah.
So actually, based on distribution over time, right? Not like regular count.
So it's a really good question. So we don't match. So technically, we don't really match. We don't do matching. So it's not like we consider each specific word from the DHS group and we match it to one specific word in the control group. We have each specific word of the treatment group to the average of the related words. But there are words fixed effects, so it's a little bit more complicated than that. But you can, okay, to a high level, you can imagine the average behavior of the average word in the control group as compared to the average word of the treatment. But we have word mixed effect. So if there is something weird that happened with one specific word, we would report that.
I think that maybe we are reaching to take this offline.
But we have, so what, that is the parallel. All we care about is that the force node and they behave similarly. Their trend is parallel.
So yeah, I was wondering, I was just trying to think about how to interpret what you just said. You know, Twitter is public. People already had no expectation of privacy yet. You learn about the government collection, and then people get affected by it. So I'm just relating this to contextual integrity.
Me
that
too.
Even if stuff is public, we expect that if somebody wants to look what I'm saying, then they have to go and look at my profile, and then they can use some tools and learn something about me. But they didn't really expect some, you know, omniscient entity like the government, in this case with Twitter, actually sucking up all the data and doing this analysis. And so then people might have realized, like, oh, okay, we did not expect the information as flowing in this particular way, and now we need to update our understanding of what's the norm in today's society.
I agree 100%. There is, one thing is expectation of privacy, but there's another thing, which is expectation of being recorded all the time. So yes, you know, I'm a Western person. I come from a Western culture, so I don't cover my face or you know, or anything when I leave the house. So I know that I'm going out in public and my face is out in the open. But that doesn't mean that I'm not concerned about face recognition now that the technology exists. Face recognition technology breaks the barrier between the public and private. It changes the equation. Maybe now that I know about face recognition, I'll just go around with a burqa around my head, or I'll just start wearing those goggles that fool face recognition. You guys know about those? I think they came out of, maybe it's paper. They're like paper frames that you can put on you know, on your head, and they just do face recognition technology.
Baseball, facial recognition, baseball cap.
No.
Because facial recognition, this is a different spectrum than vision. I put emitting diodes, light emitting diodes, and non-visible spectrums on a baseball cap, and so if somebody tries to do facial recognition, they'll just get fuzz.
Love that.
But nobody can see that you're using facial recognition. They just think, oh, you're wearing that cap.
Love it.
So I like that you looked at the anomalies based on location. I'm wondering if you considered or plan on doing a similar analysis, but not on location, but on communities of people, like looking at the network structure, or more simply, looking at identifying populations of people that are, say, journalists versus, I don't know, academic students, and they might be affected disproportionately by this revelation.
That's a great point. So what we did is we did two things. Well, we wanted to do things, we did only one. So the first thing we did is we checked for popularity. So I looked at the statistics, the Twitter statistics back in 2013, and the median number of followers for a Twitter account was 61. So we looked at accounts that were popular, meaning they have more than 61 followers, and those that were unpopular. Didn't matter much. And the other thing that we wanted to do is if we wanted to look at subpopulations, the problem is that we don't have a random sample of profiles. We only have a random sample of tweets. So we can't follow profiles over time. We don't have that. It'd be great if we had that, but you would need so this is called the Garten pose, the 10% sample. You would have to have access to all of the tweets if you want to do that kind of analysis, because we can't follow people over time, unfortunately. It'd be great. That's what people have been asking, honestly. People want to see who are these people that are concerned about their privacy. That will give you a better sense of the mechanism behind what's going on. can't do that.
Did you look the frequency of the word showing up at multiple times in a single tweet, depending on the group?
So for us, the only thing that matters is the count. So if something shows up twice, it'll count as a 2 in that particular location at that particular point in time. So we take the sum of, so if there are, let's say, 2 tweets in our data set that contain the word bomb twice at that particular location at that particular week, that counts as a 4 for us. But we don't differentiate between a tweet that only contains 1 versus others that contain more than 1. For us, all that matters is the count.
I'm just wondering if there was like an interplay between words that showed up frequently together.
I mean, we could do that. We didn't, though. Why would you think that that's? I mean, yes, I would understand why that's like you would want to know whether maybe you're thinking about topic extraction. Is that what you're?
Sort of, but also the idea of just so like a lot of food words can show up together.
Yeah.
So like chicken would show up and that'd be different kinds from things all in one.
Right.
Versus like hazmat words or something else might not show up at the same regularity with other words in that list.
I see. So we can't consider all the possible words as independent from each other. I guess from a machine, for the machine, it matters for the econometrics model, but I don't think that it matters for the machine learning algorithm. But I will get back to you.
Thank you, everybody, for coming.
Thank you guys.